Alrighty, 6 o'clock, time to go. So for those who have just joined, hi and welcome to this evening's webinar, Environmental Forensic Investigations, Protecting the Marine Environment. If you didn't catch me earlier, my name is Jane Mitchell and I'm the Outreach Officer here at ChemCentre. To get an idea of who's out there watching this evening, can I ask you to please say good day by writing your name and where you're tuning in from in the Q&A panel while I go through the introduction. Alrighty, we've created this presentation tonight, especially for National Science Week this year, based around the deep blue theme, to demonstrate the steps that ChemCentre takes to protect our marine environment. The way that we'll run the session this evening is I'll give you a brief overview of ChemCentre, then hand you over to Leif for his presentation. During his presentation, if you have any questions, please pop these into the Q&A panel at any time, and either Leif will answer them on the fly, or once Leif's presentation concludes, I'll return to run any last questions through with Leif. So, on to ChemCentre. ChemCentre has a rich culture of applied science. It has a long history of protecting and supporting the community back more than 130 years to the 1890s and the West Australian Gold Rush. In 1950, the lab gained accreditation under the National Association of Testing Authorities, known as NATA, and ChemCentre remains the longest continually NATA-registered laboratory in operation in Australia. Today, it is recognised as the state's premier chemical science facility. We provide high-quality chemical and forensic science services to government departments, industry and individuals to support a safe and prosperous WA. Now let's just have a quick look at this Q&A and see here. Hi to Catherine. All right, now it's my pleasure to pass you over to Leif Cooper, a senior chemist and research officer here at ChemCentre, to tell you a bit about himself and to present his Environmental Forensic Investigations webinar.
Hello, yes, thank you very much for having me. Thank you very much everybody for tuning in and listening. As mentioned, my name is Leif Cooper. I've been at ChemCentre for about 8 years, and before that I was been a chemist for many more years before that. I've worked in oil spill investigations, either from a forensic point of view or assisting oil spill response generally, for at least 10 years and possibly 12 or 13 if I think about it, and I don't really want to. I started, I have a Bachelor of Science from Melbourne University, even longer ago than that, and I've also done a Master's in Forensic Science through the University of Canberra, which has helped with the forensic investigation or the environmental forensics that we do, that I'll be telling you about. And now, while I get that up. So so today I'll give you a presentation on oil spill fingerprinting. It's going to chop and change and leap across a few different subjects initially, and hopefully we can tie it all together at the end. But I guess the problem we have in oil spill forensics, usually, most people, it's not normally a problem. Most ships will put their hand up and admit to spilling the oil and will assist in the cleanup. Occasionally though, you'll find a ship's captain will say, no, that's not my oil, that could be anyone's oil. And in those cases, those two statements are two slightly separate things, and it gives us two goals that we need to achieve with our forensic investigation. The first one is fairly clear and obvious. We need to find a spilled oil from the environment and show that it matches a source oil from a tank, which is straightforward. So yes, it is your oil, but when they say it could be anyone's oil, that gives us a secondary goal, which is to also show that the spilled oil does not match anything else, and discount any other reason for the spill. You really need to tie it to one particular ship, and not anyone else. So they're two slightly different things, and we'll circle back to that at the end. For those who don't know, we'll just do a brief introduction to oil, because it's important that we understand where it's from, and that's all of this prehistoric life forms. And most of it is plankton, bacteria, algae, really, really small things. Dinosaurs obviously are a part of that, but they're a very small part. most of this life is the very, very small cellular type life that when it dies in the ocean, it falls to the bottom, gets buried in sand and silt, and gradually over millions and millions of years, more and more layers of sediment get deposited over the top, and gradually the organic material gets crushed under relentless geological pressure until eventually what's left over at the bottom is oil. And if that oil gets trapped inside a rock layer, then there's a deposit that we can oil and gas companies will stick a pipe into and pump out. The important part of that is that these organic molecules, because life is such a varied, broad breadth of organic molecules, the oil ends up having quite a broad array of organic molecules. So our first problem is to try to separate all these chemicals out and see if we can pick some unique ones out of each oil. The way we do that, why am I clicking? There we go. The way we do this, our favourite tool is gas chromatography for oil spill analysis, and organic analysis generally. This is a good tool. Again, this is a bit simple. I know there's people out there who know this inside out and backwards, but for those who don't, gas chromatography comprises three parts. There's an inlet, which I've circled in blue there, squared in blue. This comprises an injector, so when I get an oil, I will dissolve it in a solvent. It will get injected into the inlet onto the column. The column is sitting in this box here. This box is an oven, which has a very high control of the heat, and I need the heat there because, of course, oil has such a broad range of chemicals. Some of them are nice and light and volatile, but some of them are really heavy and sticky, and you need to heat them up if you're going to make them, drag them through the column. I've got a column here. I don't know if you can see that. I'm not quite sure what's visible on your screen. This is what a GC column looks like. It's 30 meters long. It looks like a piece of wire wrapped around here. It's actually hollow, 1/4 of a millimeter wide, this thing is, on the inside. And you can think of the inside walls of the column as being sticky. It's not exactly what happens, but it's a good way of thinking about it. And because it's sticky, as the oven heats up, some of the lighter chemicals of the oil will boil off first. They don't stick very well. They tend to get carried along as we blow helium through the column. And so they're going to pass through the column and come out at the detector end. As we heat the oven up, the next sort of things boil off, and we'll see those coming through a bit later. The big heavy ones are going to be stuck to the wall, and even when you boil them off, they'll boil off and then stick again, boil, stick, boil, stick, boil, stick. They take a very long time to get through. The method I run takes an hour to really bake everything off, and we spread all of the thousands of chemicals that we get in an oil, spread them out over that hour so we can see a whole lot of peaks coming off as they reach the detector. This detector I've got here in yellow is a mass spectrometer, which I won't go into too much detail, but it filters out all of the molecules by their size, or at least the size of a fragment of the molecule. I hope that's enough for you to understand the next bit later on. There are other detectors we can use. A flame ionization detector is also common, which ionizes the chemicals with a flame. It basically burns everything that comes out the end of the column, which is another way of doing it. There are all sorts of exciting other kinds of detector you can use, like electron capture detector, which is very good for sulfur compounds, or halogens like chlorine and fluorine and so on, or flame photometric detectors are very good for phosphorus. They're not particularly useful for oil spills. The sulfur one maybe, because there are interesting sulfur compounds, but gas chromatography with mass spec can do the job just as well. This is what a chromatograph. So the output from diesel looks like this. We have most of the compounds are these big straight chain alkanes here, and that's because most of the organic life that deposits is fats or lipids, and those lipids break down into just the straight chain alkane. There are some very interesting and exciting things happening down here. There's lots and lots of smaller peaks coming around. These two here are very interesting. These are my second favourite compounds, pristane and phytane, and they are the two most readily visible biomarkers. And biomarkers are the things we're looking for in oil spill analysis. What's a biomarker? Biomarkers are things that we can tie, they're molecules that exist in the oil that we can tie unequivocally back to compounds that were found in the organic life that deposited back millions of years ago before we crushed everything and turned it into an oil. So if we have a chlorophyll molecule here, this is likely found in early plant life and even in early plankton and algae and so on. So there's a fair bit of chlorophyll that would have been deposited in the ocean floor. And once you get an oxidizing environment down the bottom, we get a bit of a cleavage happening at this point, and we saturate these double bonds for those chemists who can spot that and understand. And what we end up with is this pristine molecule. If the environment you're in is not quite so oxidizing but a bit reducing, then the cleavage happens in a slightly different spot because you get slightly different degradation. And so we get phytane instead. And so those two peaks I showed you in the diesel chromatogram earlier, pristane and phytane, don't always turn up at the same ratio. Usually pristane is slightly higher than phytane. If it's an oxidizing environment, then pristane is going to be quite a bit higher than phytane, and you might not see very much phytane at all. If you have a reducing environment, you'll still see quite a bit of pristane, but the phytane will be more pronounced. And so we can look at a pristane-phytane ratio as an indication of what the redox potential of the sand that it was deposited in eons ago. And because every geological deposit had slightly different oxidizing environments, in theory, every different oil is going to have a different pristane-phytane ratio. In practice, a lot of them are very close and it's a bit hard to see. So while it's good for distinguishing some oils from others, we're going to need a few more biomarkers. Fortunately, there's plenty. So bacteriohopane tetrol is very common, and there are lots of ways in which this breaks down into many different things. Clicking along. So this molecule is hopane, and this is what it usually ends up as. This is a very easy to find molecule in crude oil because of its size, because of its stability. All those hexagons, the cyclohexanes, are very, very stable, which makes sense because if it's been able to resist eons of geological pressure, I'm not going to have any trouble finding it after an oil spill. Except sometimes it cleaves a bit differently. Again, if you see these bishopanes, homohopanes, these things come when cleavage happens in slightly different spots because there are slightly different oxidizing potentials in the soil, or perhaps the organic biodegradation has happened and there's a particularly rich bacterial content in the soil, and so we get more these smaller things happening. And so those crude oil deposits are going to have a slightly different profile of hopanes. Or even you might get cleavage of this hexagon entirely and you get this triterpane here. Moritane is another interesting one to do with the age of the deposit. The R and S's, these big ones turn up in pairs because this molecule, this little methyl group here, is sticking up, if you like. Most of this molecule is flat, but this methyl group sticks up. And in this molecule, its partner, the methyl group, sticks down. You can think of it as a mirror image. These two are mirror images of each other. Originally in the life form, everything was this R version, or this R version. Over time, geological ages, some of them will flip. And over even more time, some of them flip back. But to start with, it's all R. By the time it's a crude oil, you'll get about 75% R and 25% S. If it's a really, really old oil, those ratios start coming closer and closer to 50-50. So we can look at these pairs, 31 ABR, 31 ABS, or 32 ABRS. That's another ratio which is indicative of age, rather than pristane phytane, which is indicative of redox potential, or trigonal hopanes, which are indicative of bacterial degradation. Or other biomarkers like these steranes, sterols, which turn into different stigmastane and ergostane. Depending on what kind of bacteria you have, you might have a different level of stigmasterol compared to the campesterol, or vice versa. And so you get different stigmastane-ergostane ratios. These are all biomarkers that are relevant and change depending on the depositional environment. What I've got on the right here is a few smaller molecules, polycyclic aromatic hydrocarbons. 2-methylphenanthrene, 3-methylphenanthrene, 2-methylanthracene. They're all about the same size. They all come out very close together in the chromatogram. What's interesting is that methylanthracene, the bottom one, isn't normally present in a crude oil. And so we would normally not see that. But higher methylanthracenes do exist. And when the oil goes through a refinery process, the methylanthracene gets formed. So it's not, strictly speaking, a biomarker, but it's a distinguishing feature of a refinery process. And so the presence of methylanthracene firstly indicates that a refinery process has happened. Secondly, depending on your refinery process, how that's worked, you'll get a different level of methylanthracene compared to the methylphenanthrenes. And possibly depending on what higher anthracenes are even present, you may or may not get it as well. So it's yet another distinguishing feature. These are just a few examples, which give us a lot of biomarkers. Traditionally, if we're picking out biomarkers that give us a fingerprint of the oil, you want a lot of biomarkers that have a distinguishing power that you can see, that give you a profile that is hopefully unique to that crude oil. Also, the problem with a spill is that once you've actually sampled a spill in the environment, it's no longer the same oil as what it was when it got spilled, before it got spilled, because the tank is nice and sealed and closed up, but the environment is not sealed and closed up. And so volatility is an especially difficult thing to handle, because all oils will evaporate to some degree. So the lighter ends of if you've got a biomarker that's particularly light and volatile, you're probably not going to see it by the time you sample it. That volatility happens across a day or two. You can lose up to 40 or 50% of the oil if you don't get there within a day or two. And I've seen some spills where up to 80% of the oil is evaporated away by the time you've sampled it. Biodegradable, some of the compounds we see do get actually eaten by bacteria. And that's a problem for us. Remember, the goal here is to show that the profile, the ratios of compounds that we choose in a spilled oil match the ratios in a sample oil. And if they're different because of biodegradation, it's harder to explain that in court, because what you really want them to be the same, and you can then show a judge, look, see, they're the same. And if they're different, that can pose a challenge. Some compounds are soluble, and you kind of want to steer clear of those, because almost all oils are spilled at sea, and the sea is water. So these slightly soluble compounds will get reduced in the spilled sample compared to their concentration in the fresh. And photooxidation can even happen, especially with for example, the phenanthrenes, the polycyclic aromatic hydrocarbons. UV light starts to destroy those and turn them into epoxides, and then they become they disappear as a result of that. So traditionally, we've avoided picking those biomarkers, and we've tried to stick to the stable ones. The Hopane series that I started with is a very good one for that. The steroids are very good. More recent research says, rather than avoid them entirely, what we can do is let's use all of the biomarkers, but understand which ones, whether, and how. So nowadays we leave in phenanthrenes because they're interesting to see, and if they do happen to be reduced, we can say, well, they might be different from ratio from the sample, the source, because it's a different oil, but it might be actually the same oil and there's been photooxidation. And if we suspect that case, then what we've also got is a series of other biomarkers that also photooxidize, and we can go and check those. And so we'll go to methylfluorines, or we might check out the dimethylfuranthines. And if all of these photooxidizable biomarkers have all reduced by sort of a consistent level, then we can say, oh, okay, look, they would be all about right, but there's been some photooxidation happening, and everything else would make sense. So that's a relatively new concept in spill forensics. This chromatogram is an absolute mess, but hopefully it shows there's 145 compounds in there, and these are all of the biomarkers that we look for that give us a really unique profile. Hopefully every crude oil is unique. Here's an example, just a total scan of an actual spill, which I cannot say where it's from. And what I've done here in black, I've got the spill. In each case, I've put the spill in black on each time. And in green, I've got a potential source. And so the total ion chromatogram is what we call this. This is just a big look at everything that's in the crude oil. And we can see that there's, hopefully you can see this at home. It's relatively easy. This one down the bottom here looks very, very similar, as it should, because what I've done here, this is a spill. In green is another spill, but it was about 20 kilometers down the coast. So sometimes you've got to make sure not just that the spill matches the source, but that all of the spills match the source, because another argument in court is, well, yes, we made a small spill in the harbour, but the spill down there is somebody else. So sometimes you've actually got to match multiple spills to the same source. The top one here was from a waste oil tank on one ship. This one over here is, again, a waste oil from a separate tank. Certainly these three peaks here don't match crude oil. We didn't end up working out what they were, but there's some very strange things going on within this crude, bunker fuel or waste oil, whatever it is. And this one down here is from a third ship, and it's checking my notes, sorry, a heavy fuel oil. So this is a bunker fuel, and bunker fuel's gone through a refinery process, or part of it's gone through a refinery process. You'll find this bit up here is just the heavy residuals, and then they've deliberately added diesel back into it in order to give it a viscosity, which is why we're getting such an interesting, well, to me, it's an interesting array of compounds. So we can see that these two match, which is nice and easy because that's a spill and that's the same spill, but further down. And I'm inviting you all to have a think about which of these three sources might be the actual source. And it's difficult to see from a total. So what I'm going to do now is show us the Hopane profile. So I'm using the mass spectrometer to filter out all of the other compounds, just focus on the part of the chromatogram that has Hopanes. And we can see, first of all, down here, the spill number 1 and spill number 2 match. And so we can look at 30 AB is there, and Moritane is there, and 31 ABR, 31 ABS. These are the RS pairs, RS32 RNS, 33 RNS, and so on. Some lighter triterpenoids here. Every peak matches, pretty much, all the way along there. And if you peruse the others, you'll probably work out fairly easily. This one doesn't match. This one doesn't match, especially in this region, but this one does. We've got some nice peaks here, these two peaks. This oleanine peak is quite high. Gamma serane was quite high as well. And so from that, we were able to, first of all, we can say, yes, this in ship number 2 here, your waste oil tank matches the spill, and no other tank matches the spill as well. You are the only possible source of this spill. What else have we got? Beyond the fingerprint. So we also want to look for other compounds. It's important to understand that the fingerprinting and that kind of work is only a small part of the overall investigation. The other thing that's interesting is to go and look for some other compounds. There might be some strange and unusual biomarkers that turn up. Maybe that's there's bicatenanes or lupanes or something else strange, hexamethyl chicken wire or something like that. If you see something unusual in the spill, go and have a look and make sure it's also there in the suspect source. It can be another unique thing that you're looking for. Solvents are sometimes used. We did manage to solve one case where 2 ships had refueled at the same port from the same terminal in very close succession. So the oils in their tanks were very, very similar, and that made it a bit of a challenge. There were some slight differences because the oils that they've taken on board have mixed with a half full tank already. So there were a couple of differences, but not as many as I would have liked. But the ship that had had the spill had spilled it on deck and had used a solvent which contained dichlorotoluene to clean the deck, and that dichlorotoluene ended up in the waste tank, and it also ended up in the water. So we were able to see dichlorotoluene in the spill samples, which was unusual because chlorinated compounds aren't normally in an oil. And there was also the dichlorotoluene in the bilge still of the ship. but there was no dichlorotoluene in the other ship. And so we were able to narrow down which ship it was using that. A bit of extra evidence to show that I was right. And mixtures can be a real mess. I've mentioned waste oil tanks. Sometimes waste oil tanks are actually some diesel, some of the crude oil, some of the fuel oil, some other transmission fluid that they've spilled and just chucked in. And that mixture, because each of those mixtures has their own profile of biomarkers, gives you a different and unique biomarker profile again. And if they tip all of that waste oil tank out into the ocean, there may be none of the original mixture left on the boat. But if you can find the original oils that made up the mixture and can do a bit of maths and work out what the ratios would have been, you can possibly do it. It's very tricky, but it's possible. What else? Beyond, it's also important to remember that the evidence that we would give here is just a small part of an overall investigation. And so we'd be assisting investigators and prosecutors with all of their evidence. It may be a bit pointless to do a fingerprint when you've got something like this. This is footage from Channel 7 of a spill in Fremantle Harbour in January of 2019. And you can see quite clearly the sea chest here has been flushed, and all of this oil is leaking out into the Swan River. And the name of the boat is quite clear in the top corner there. It's very hard for the captain of the Naumer to pretend that he didn't spill anything. Spill modelling is an interesting part normally of spill response. If you've had a spill and you know where it's from, you'll get some spill modelers to predict using the properties of the oil, the ocean currents that they know of, the wind that they're expecting, and they'll work out from a point source, where is the oil going? And so they might get a graph like this, which tells us, this is sort of where we're expecting. So get out to this beach here because it may be that this beach is going to be affected in a certain amount of time. In an investigation, we can do this the other way around. And it was done quite well in North Queensland a few years ago when oil started washing up on beaches near Cape Upstart. And so they tracked when the oil turned up on which beach, and use those observations to run the model backwards and take it backwards to when all of these oils turned up from a single point. And the single point happens to coincide with the very narrow shipping channel that goes through the Great Barrier Reef. And they guess that it's around about the Tuesday morning or whatever it was that the spill must have occurred within a very small section of the shipping channel. And then, of course, the Great Barrier Reef is well monitored. We know what ships are there and when they are. So the investigators were able to narrow down to about 4 ships rather than about 17 that were sort of in the wider channel. What else can you use? Oil record books. Every ship has to have an oil record book, and it's a pretty blunt sort of tool. But if you transfer oil from one tank to another, if you take on fuel, if you use it because you've steamed from Darwin to Singapore or whatever, you note it down, and you do have to keep track of all of the oil movement on your boat. And those records can be seized by investigators, and the tanks can be opened up and looked at. And if the oil record book says that you've got 30,000 litres in a tank, and we open it up and there's only 20,000 litres, someone's going to want to know why. It's also worth, in an investigation, if you're doing one, have a look and see if there are any satellites overhead. This image is a satellite shot of the Wakashio, which is currently parked off a coral reef off Mauritius. This was only taken last week. And there's plenty of satellites up there that are doing marine monitoring, either in the visible range like this, or they might be doing infrared range monitoring or temperature mapping or whatever. It's worth asking around and seeing if there are satellites around somewhere, and they can spot boats and they can spot oil. Part of an investigation, and it's useful. And I think I'm done. That's all from me. Back to you, Jane.
All right, Leif, thank you. We do have one question from earlier on. Catherine Ling. What is Leif's
my favourite
compound?
The hopanes. I forgot to mention that in the end. So yeah, pristane phytane, second favourite, but hopanes are my favourite. Thank you, Catherine.
Beauty. I've got a question for you. Between a spill and a prosecution, what's the kind of the longest, time frame that it's taken place in order to get to the end point there?
Sometimes 3 or 4 years for a straight-out investigation, but beyond that, you'll then see people who have been affected by the spill will want to claim compensation from that, and there may be arguments over how much damage has been done. So, and that's a different kettle of fish. And I guess the longest one I can think of there is straight off the top of my head. I did some work for the Montara oil spill that happened in 2009, and there were in the Timor Sea. And whether that oil reached Indonesia or not is a point of contention, and there are Indonesian seaweed fishermen who are still pursuing action in the Supreme Court, and that has not yet finished, and that's 11 years ago so far. And we're still not going on. And many others have taken, I think Exxon Valdez had court cases for years and years and years and years. I expect the Gulf of Mexico spill is another one where we will continue to see claims for many years in the future.
Okay. We've got a question from Michelle Sexton. What size samples need to be collected from a spill to be able to be analysed?
To run a spill through the chromatogram, I need to have 5 milligrams of samples in the vial. Milligrams. It does not need very much at all. So, and this is helpful because a lot of times what you're seeing there is a rainbow sheen on the oil, which might be only nanometers thick, and all you can really do is sort of scoop a jar and hope that there's a little bit on the top there, and that's enough. And we can usually extract that and get a profile from it. It does not need a lot.
And I've got a follow-up one there from Michelle. Is the fingerprint affected once chemical dispersants are used?
Dispersants would, I guess, probably not. Things that are soluble will become, it would accelerate the weathering process. I think that's the thing. So volatility stops being an issue because you're not exposed to the air, you're now subsurface, but it's also broken it up into many, many smaller droplets. So solubility is greatly enhanced, hugely enhanced, and bacterial degradation will start to become hugely enhanced as well. So yes, the profile changes, but the basic hopanes and stearanes, the ones that are really resistant, they're probably still going to be the same. We're going to start to see losses of alkanes. We'll start to see losses of the naphthalines and methylnaphthalines through solubility, and we might even start to see biodegradation of the next things, the higher alkylated phenanthrenes and so on. That's an interesting question. Yeah, well done.
Okay, I've got another one from Catherine. How many oil spills would you be identifying in a year?
Fortunately, there's not that many because there aren't that many spills, which is a bit sad for me because I don't get to do interesting work, but it's a good thing overall because we don't want oil spills. The best way to clean up an oil spill is to not have it in the first place. So some years, sometimes you get 3 or 4 in a row. 2019, I only had 1 or 2, and there's been 1 or 2 this year as well, roughly.
Cool,
and
thank you.
Not all at sea, sometimes they're at land.
Beauty. I'm just going to do a little plug here while we stay open for a couple more minutes and see if there's any more questions. I'm just going to say thanks for joining us today. This is our website. If you would like to be involved and see what other news and events are around, just jump on our website, come to news and events, and you'll find them here and here. If you would like to join our mailing list and find out what things we're up to and what kind of news we'd like to share, this is another way of staying in touch, so you can sign up to our client newsletter here. So I shall return to Leif. There's one last question. More of a statement, actually, from Michelle. Thanks, Leif, for your answers.
No problem.
Leif, are there any other pearls of wisdom or anything in particular that you're passionate about, or anything exciting that's coming up that you just wanted to share in the last couple of closing minutes?
You asked me this last time. I wasn't ready for it. No. Look, if you're out there and you want to try to catch a spill, please make sure you write good notes. We mentioned it, 11 years, 10 years, 11 years between a spill and a court case. You're not going to remember what you did in 10 years' time. So please take a good notes, good documentation, and yeah. If you're doing it, that's the logistics is sometimes the hardest part of a spill response, rather than the science.
Beauty. Okay, well, I think we'll call that one a wrap. What do you reckon, Leif?
I'm fine. Thank you very much.
Yep. Beautiful. All right. Well, thanks to everybody for tuning in tonight. We appreciate your attendance. We hope you've enjoyed this experience and learnt a thing or two about environmental forensics, about Leif perhaps, and about the role that ChemCentre plays in keeping our marine environment safe. Yeah, we're signing off, and have a good evening.
Thank you.